Hello, and welcome to the second video for Chapter 10 from the Physics of Everyday Phenomenon by Griffith, 10th edition. Okay, so we are in section 10.3, Joule's experiment and the first law of thermodynamics. Now, I'd recommend you watch that first video first, okay? It's the first of what's probably going to be 4 videos covering thermodynamics because this carries over to chapter 11, next chapter, okay? This will be a video that will conclude, this one will, chapter 10, okay? So we're going to pick up where we left off. We had 3 definitions in the last video. I expect you to know those. I hope you know them. We've got heat, specific heat, and temperature, okay? Now, specific heat has a similar quantity for phase changes called latent heat. So technically it's 4 things, okay? We defined absolute zero, something called the 0th law of thermodynamics, but in terms of ones that really matter, that kind of just give us an important conceptual view of the physical world, the first law is a good one, okay? The first law of thermodynamics. And historically, we get there through this interesting experiment, okay? So Rumford noticed that cannon barrels became hot during drilling, okay? So that friction was delivered to the metal got hot, okay? Joule performed a series of experiments showing that mechanical work could raise the temperature of a system, okay? Delivering that work and the resulting energy into the thermal energy of water, okay? And why water? Because water, is starting to become well understood at this point in history in terms of knowing its exact properties and it being a sort of replicable experiment. Other people can work with the same substance, okay? It's an obvious standard liquid to use here, all right? This paddle is just gonna stir up the water. It's not gonna heat it up much, but it will. It has to deliver some energy, all right? In one such experiment, a falling mass turns a paddle in an insulated beaker of water, producing an increase in temperature, a measurable increase in the temperature of the water. Some fraction of a degree Celsius usually, depending on how the setup works here, okay? Are there better ways to deliver energy than spinning the paddle? Turns out there are, absolutely, because you can have it with friction in a metal, you can have a more obvious change. But overall, the energy has to go somewhere. And in this case, you just have to worry about a significant amount of it going to the pulley, perhaps, right? Some of it go to air resistance, but ultimately, that heat is going to get delivered. So it's trapped within this body of water, and you should measure that difference. This is an experiment that's replicated in classrooms, right? So we can actually see some larger scale equipment here, setting up an experiment. So Rumford's, this is the cannon drilling. So that's just a painting of the observation. Okay, so this is going to get us right to the first law now, all right? Because we're thinking about energy being converted from one form to another. In this case, it was mechanical work, the work done by gravity to pull the mass down, getting converted to the thermal energy of the water, okay? The water is raising in thermal energy. It's gaining thermal energy, which is something we haven't actually defined. We're just about to. It's going to show up. We're going to ask ourselves, what is thermal energy, okay? And it's like potential energy for mechanics, but it's for this study of heat, and it's the heat energy that an object or a substance can possess, okay? So Joule's experiment led to Kelvin's statement, Kelvin like the temperature scale, of the first law of thermodynamics. Both work and heat represent transfers of energy into or out of a system, okay? So remember, these are both terms that refer to the transit of energy. We use one for mechanical systems, macroscopic. That's when we use work, right? The work done by gravity on a ball, okay? When we talk about heat flow, it's things like cooling off water. It's like a hot piece of metal conducting heat through a panel. It's the energy of sunlight hitting something, right, and warming it up. Those are all cases of heat, right, where we wouldn't use work, right? Instead, we would use heat. But ultimately, it's all about the flow of energy. If energy is added to a system, either as work or heat, okay, sometimes both, the internal energy, because you can deliver work and heat, right, of the system increases accordingly, okay? So if you deliver these things in, then there will be an increase of energy inside the system, the internal energy, okay? I was calling it thermal energy. That's a term that's used plenty. Calling it the internal energy also, okay? Internal thermal energy, all right? And it's represented right here by the letter U, all right? We used P or PE for potential energy, and we had the two forms, elastic as well as gravitational. So similar, right? But we're not using P, we're using U, okay? U for internal energy. It's the energy that the object possesses, right? This rock or potato or clump of clay, it's got some work being done on it, and it's gaining heat energy, okay? So therefore, it's gaining internal energy. There's a net increase in its internal energy, measured in joules. Now, we know that it's gaining heat, which is Q, okay? We mentioned that in the last video, I mentioned that in the last video. And we know it's gaining work because of the direction of the arrows, okay? This curvy arrow, kind of indicative of maybe radiation or a wave of energy, right? We'll talk about that when we talk about one of the key ways that energy flows from point A to point B, indeed is electromagnetically, as light, which we don't know is an electromagnetic phenomenon yet, but we will soon. Regardless, we definitely know it's a way that energy moves from point A to point B, okay? And that's actually, we'll get to that in the last few slides of this lecture right now, okay? But point being, right, not to go off on that tangent, is the heat is flowing in there, represented by the letter Q, and the work is flowing in, but it's shown as a negative, yet the arrow points inwards. That's because of the way the formula is written, okay? So this is the first law of thermodynamics, and I think it'll be easiest for me to discuss it if I go over here. So yeah, it's just going to be better to look at the first law of thermodynamics written out, where I can clearly show those variables. Okay, so what we have here is we've got this delta U term, all right? That's usually written over there on the left. And then there's a difference that's shown on the right. So it's the difference of two terms, all energy terms. And so this is just going to be Q. I'm going to add a subscript to that, by the way, which you know your book doesn't have. It just wants to keep things simple. But here, just think of the subscript as honestly just that. It's to serve as an explanation. It's to clarify, right? If you remember what it means, then it's always going to be the same. So Q has that meaning. But what that subscript is just the word to, all right? Because Q represents heat, and that means that this is the heat added to the system. I'll add labels in a second. And then we have minus W, similar subscript, by, okay? So to elaborate on that a tad, let's label these down below, okay? So this is the change in internal energy, change in internal energy of the system. That's usually what we call it, you know? I might call it a substance, I might call it an object, right? But it's the system. Sometimes it can actually consist of multiple parts. That's fine, because you can have heat flow between them. You can have multiple things all reaching thermal equilibrium, and so you can deal with those processes. This term, the one I mentioned, the heat term, this is heat added to the system. So heat added to the system. Okay, and then this is work done by the system. And this concept of the system doing work is going to set us up nicely for understanding the second law of thermodynamics and taking our focus onto heat engines, really applying this to some sort of cyclic process, because that's what it's all about, is that we can end up getting useful work from thermodynamic processes. That's what combustion engines give us, that's what steam engines do, that's even what boiling water in a nuclear power plant does when it takes that boiling, gaseous stage of water and phase changes it back to a liquid and in the process, at least cools it down, and in the process spins turbines, turning that heat energy, chaotic energy, into useful rotational energy that then immediately gets converted into electromagnetic energy via a spinning coil inside a magnet that's connected to the spinning turbine being driven by, well, this term right here, the thermodynamic work. All right? Itself driven by a nuclear release of energy, right? So talk about converting one form of energy to another down the line. So work done by the system. So the fact that the two terms on the right-hand side are a difference makes sense, because if you have your Q2 term, Q2, right? So the heat added to the system term, if that's bigger than the work done by the system, well then your net change is that your system warms up, okay? And I say that, what I mean is that it has an increase in internal energy. Now it turns out that those things are the same. There's going to be a direct relationship between increasing internal energy and warming up for some substances. The most classical example is ideal gases. So that's a case where we have a really clean relationship between change in internal energy and the temperature. So let me show you that, and I can actually add it in to our graph. Okay, so over here, right? So of course this is the law we're talking about, first law of thermodynamics. We moved on from Joule's experiment. That was just a launching pad to discuss this. We introduced the concept of internal energy. An increase in internal energy may show up as an increase in temperature, so as I was just saying, or as a change in phase. Okay, if there's a phase change, until that phase change is done for whatever is the system, usually assumed to be isolated or insulated from the external world, well, once the phase change is done, then you can start increasing temperature again. But you're going to have to phase change the whole substance, right? You can't phase change some of it, increase the temperature of the rest, right? Not in idealized systems. Okay? And there's going to be so before there's any other increase in the kinetic and or potential energy of the atoms or molecules making up the system. That's an important little statement there, because that's reminding us that kinetic and potential energy, mostly kinetic is what I've been talking about, potential plays a role, is what's going on in terms of actually containing that internal energy. All right? The molecules are bouncing around in the case of a gas. The molecules are kind of elastically jiggling around in the lattice of a solid. All right. The internal energy is a property of the system uniquely determined by the state of the system. So it can look very different for very different substances. Imagine like a diamond, a very rigid solid, compared to a gas. The way they manifest changes in internal energy is quite different. All right. The way that the amount of energy that corresponds to temperature, all these things can vary quite a bit between all these different materials. And the broad subfield of material science, this is one of the things that they investigate, along with, of course, which things are conductors and so on. So the internal energy of the system is the sum of the kinetic and potential energies of the atoms and molecules making up the system. That's a broad, true statement. It doesn't tell us what all the incredible amount of different types of intermolecular forces we can have and so on. I haven't focused on the potential energy. That's certainly part of it, because it's not just random motion. It's the fact that you might have charged particles that are opposite in charge and are attracted to each other, but are naturally being held apart, and they have a potential energy to move towards each other. So at any given point, the sum of all the energy in a system of trillions upon trillions of particles is going to be some of it contained as potential energy, things that are about to fall, and then other things that are in full speed motion because of whatever forces are driving them, whatever potential energy gradients they exist in. Gradients is just a term for like slope, right? Like imagine a topo map, it's all those slopes, but here all the slopes are forces, like a vector map. So a hot plate, getting back to the basics here, is used to transfer 400 calories, one of the ways we measure energy, of heat to a beaker containing ice and water. 500 joules of work are also done on the contents of the beaker by stirring. Okay, so we're putting some energy in. Now again, stirring is not going to be terribly effective here, because it's probably just that whatever energy it adds can be pretty much easily dissipated. It's difficult to insulate for such small changes in energy. So we're going to have conduction, as we'll learn about in just a second, into the wood, right? We're going to have radiation into the air, maybe a little bit of convection, which is just the bulk movement of fluids. So yeah, good luck actually heating it up, but we're going to say it's idealized, all 500 joules are getting delivered, or maybe this is just what manages to get delivered with some sort of built-in inefficiency. The question, however, is what is the increase in internal energy of the ice-water mixture? Watch your units, okay? Uh-oh, our options are in joules, right? Which is tricky, right? Because we were given 500 joules over here, right? And calories over here. What's our relationship, right? How many calories are there in a joule, right? Right. Well, every calorie is about 4.186 joules. Okay, so 4.186. So essentially, that means what we're looking at here with the 400 calories is about 1,600 joules. Right? We're adding it in. Think you can work out the rest? What's the answer? Okay, I'm going to show the answers now. All right. So we have a value of work. Okay, which is going to be negative 500 because we're putting it in, okay? That just means our negatives are going to cancel. Another way you could write that, right? I don't mean to confuse you. I'm actually trying to give you a reasonable option. If it seems overly clunky to have to put the negative in knowing it's going to cancel, well, the idea that work by, that it's negative when it's coming in, right, is exactly the same as saying that work by equals the negative of work on. Right? And that's in this example, as well as the figure we saw, with the incoming arrow, that is work being done on. All right. So work on is the negative of work by is the negative of work on. Right. They're just opposites of each other, same in magnitude, opposite in sign. They're both scalars. Right. All energy is scalar. It doesn't have direction. So that means we could actually substitute that in, rewrite this, right, as the change in internal energy of some substance, okay, in this case, beaker water, is equal to the heat added to it, which was 1,600 joules once we converted from calories, plus the work done on it. See? Two alternative ways to write the first law of thermodynamics. Okay? Both are equally right. First law of thermo, slang for short thermodynamics, right? Okay, so with that in mind, right, we see then that our total is just going to be 1680 plus 500, which is 2180. D was the correct answer. All right, so now we have a hot plate that's used to transfer 400 calories of heat to a beaker containing ice and water. 500 joules of work are also done on the contents of the beaker by stirring. How much ice melts in this process? So this is interesting, right? Because before, we were just solving for energy. We just had to use the first law of thermodynamics. But now, we have to do one more step, okay? And this step simply involves using one of the equations that we saw in the first lecture video, or the earlier slides, or sections 10.1 and 10.2, specifically 10.2, and that's the equation for latent heat capacity, okay? And the corresponding heat equation, which has the units that we need, okay? Now we need to know the constant and a few other things, so I'm gonna remind you of the relevant equations, okay? So if we go over here, we definitely want to use this one, so I'll number these as the equations you need to answer the current concept question, not really at all, a numerical question. Okay, so here's equation 1 that you'll need. The other equation that you're going to need is hopefully familiar, unless you're watching this video first, and that's the idea that the heat it takes to do a phase change is Q, all right, and it's equal to a material-specific constant called the latent heat, in this case of fusion, because we're melting ice. It'd be latent heat of vaporization if we were phase changing from liquid to gas. That's boiling, essentially, right? So latent heat of fusion, and then times the mass. Okay, so this problem up front seems to be lacking in information, right? Because we're not told how much ice there is, right? We're told it's a mixture. What does that mean? Like, how? Don't you want to know how much there is of each? But we're to assume there's enough, okay? So there's enough ice that not all of it melts. So whatever is the correct answer of these options, we know that there's going to be more ice than this, because otherwise we'd have to worry about the fact that the phase change is done, and then if there's any leftover energy from this, what we now know is an input of 2180. If any of those joules are left over, then they're actually going to heat what is now all one phase of water, all right, H2O, all the liquid phase. And it'll heat it up according to the specific heat capacity, not to the latent heat capacity, all right? Similar quantities, both customized to water, okay, in these phases of solid and liquid. Okay, so we don't want that. We'll keep it that we just have the heat being delivered to that phase change, okay? And our unknown is M. Our unknown is the mass of the ice, okay? Because, believe it or not, we know Q. We know Q because it's just going to be not even Q2, but it's actually going to be the sum of them. Because here, in the equation, and we actually used Q, okay? You might be like, oh, well, then it's just equal to that value, it's the 1600, but what about the work on? Because that's also energy. The only place that energy has to go is into the water, or the ice liquid water mix, okay? The only thing it can do is phase change the ice until it's all melted, okay? And the reason you can have a mix is because they're just both at 0 degrees Celsius. You can definitely have different phases at equilibrium at that temperature, okay? So until they're all changed. Okay, so that means that really here, we rewrite the equation as delta U, right? It's a variable representing, in this case, all the energy being added, okay? Because when we first saw this in the last section, it was the energy being added to the substance to melt it. Well, that's the change in internal energy, okay? A little confusing, actually, but So that's what we have, right? That's what we have to deal with. So it's delta U equals latent heat diffusion times the mass of the ice. Okay? So that means that all we need to find is the total energy that's added, okay, which we know to be, I'll remind you of the number, 2180. Okay, so that's the input of energy in joules to our ice-water mixture. Now the latent heat of fusion, that is one you'd have to look up, but I'll give it to you here. It's almost 2100. That's the specific heat capacity of ice, but we're not heating the ice, we're just melting it. It's 333,000 joules per kilogram, okay? And then you got your M. So then when you solve for this, it's going to be in kilograms, and it looks like we'll have to convert it back over to joules, okay? So showed you the steps there, but go ahead and still solve for it. All right, ready for the answer? Here we go. Okay, so they have it, right? They actually put it in calories, and then they have the 4.19 joules per calorie. Okay, and then we have, yeah, the 2180, which we used as well. Okay, same sort of thing. So what I wonder though is they're gonna have theirs in joules per gram. Oh, I see, no, they do convert over. So they start off and they say, okay, hey, it's gonna be, this, they're saying this is a known quantity, the latent heat of fusion in calories per gram. The one I know is that 333, okay? Now notice that theirs is 335. I'm not sure what the key difference is there. And you might be like, why isn't it hundreds of thousands? Well, joules per gram, mine was joules per kilogram, right? Difference of 1,000, right? So theirs is 335, mine is 333,000, right? Joules per kilogram, right? Let me show you that one more time. There it is, 333,000 joules per kilogram. Same value. Okay, now we're going to solve for M. Okay, so they go ahead, right, acknowledge that number, say that, hey, now we know delta U over L, start with that, right? And then the fraction is just 2180 joules divided by that 335, and we get 6.5 grams. Okay, that's how much ice melts. It was C. Okay, good example. So consider a gas in a cylinder with a movable piston. Okay, if the piston is pushed inward by an external force, that's work being done on the gas. Okay, like if gravity is pushing it, or some external force, right? Maybe its own inertia. That adds energy to the system. What's the system here? The system is the gas in the cylinder. The system does not include anything outside of the gas in the system. Okay, it's the working substance is the system. The working substance is the gas. Okay. So the force exerted on the piston by the gas equals the pressure of the gas times the area of the piston, okay? So we got a really nice relationship then between pressure and area, okay? Which means that we have a nice relationship between volume and, and pressure, okay? Because the work done equals the force exerted by the piston times the distance, okay? We know that the force is just pressure times area. Think Pascal's law, right? In the previous chapter, chapter 9, if you want to remember why this is true, okay? Force is pressure times area, and we know the pressure has to be uniform everywhere. It's conserved, okay? Same principle that allows us to build a hydraulic device, but in this case, feeding into other concepts, okay? Feeding into this conservation law, the first law of thermodynamics, right? So, as I was saying, the work always, by definition, is force times distance, as long as there's no angle between them, okay? Which we're simplifying it, and it works fine here, right? Because the piston can only move one way, right? So force times distance. Replace the force with pressure times area, okay? What you get then, well, what happens when you have area times distance? It's not even a nice uniform shape, right? It's not a cone or something, right? And it's a cylinder, right? So as long as it's uniform along the movement of the piston, okay? Which of course is going to be, right, if you manufacture it. Then biology does it differently, I suppose. Then we end up with pressure times change in volume, because that A times D is just that change in volume, okay? Okay, that's great, because that means that the work done either, in this case, on the gas, if we're looking at the figure, or what if the gas itself is expanding, right? If it explodes, think of combustion engine, it pushes the piston out. That's the gas doing work, okay? And the work done by the gas is precisely equal to whatever is the pressure at that moment times the change in volume of the gas, okay? So if the gas is being compressed, the change in volume is negative. Thus, the work done is negative, all right? That's work being done on the system, okay? Work being done on the system is negative by definition, okay? Negative work increases the energy of the system, as we know, right? We saw that, in the equation, right? We saw that precisely when we were stirring it. We were doing work on that water by stirring it, and we were increasing its internal energy, which could do things like elicit a phase change of ice. If the gas is expanding, positive work is done by the gas, See, gas can do work, absolutely, right? Okay, maybe because heat's being added to it, maybe because chemical energy is being released, right? And the internal energy of the gas decreases. And notice I kind of threw that in, right? Because you think of a combustion engine, what happens there is a chemical reaction to release the energy that was in these chemical bonds. You can even release nuclear energy or create an explosion, obviously. But whatever release of energy there is, that would be included in internal energy in a broader sense, right? Because here we're really just thinking about internal energy as being motion and potential, and not focusing on the microscopic, the atomic, and the nuclear scale. Okay. So ideal gas. The ideal gas is a gas for which the force between atoms are small enough to be ignored, so no potential energy. That's cool. That means that all the energy that gets added to the system ends up becoming the kinetic energy. That's a great model. It's so much easier to work with than, say, a model for a solid where you can have all that elastic potential energy and electromagnetic potential energy. In this case, all the particles are neutral, so there's really not a lot of charge between them. We'll talk about charge later, okay? But if you're familiar with it, right, and it creates currents in our walls, right? So it's charge, But there's none of that here. This is just a bunch of literally neutral balls bouncing around, bouncing off of each other. All the energy is just conserved. The kinetic energy, because of all the elastic collisions between the particles, and so then what you're left with is all that energy manifests as heat on the macroscopic scale and as motion of little individual particles on the microscopic scale. Ideal gases then must be really simple gases. So they end up being things ideally that are actually monatomic gases, like monatomic hydrogen and monatomic oxygen work pretty well. Hydrogen's the best, obviously, because it's so simple, just being an individual proton and neutron. You can even have a plasma, which is ionized hydrogen, then you just have a proton by itself. And so that's a case where you can have, again, what would be a pretty good match to an ideal gas. The other types of gases that are often considered ideal gases, depending on the level of the class, are diatomic gases, which is like H2, O2, N2, diatomic nitrogen. In the case of N2, O2 is diatomic oxygen. Those are common naturally forming gases, and including H2. And so with those, we end up with a case where the diatomic ones for those small molecules are pretty close in behavior. So sometimes they're the go-to, hey, we'll consider this an ideal gas. And it's a pretty good match, okay? All right, so absolute temperature is directly related to the average kinetic energy. There's nowhere else for the energy to go, all right? Because remember, the energy, or the temperature, I should say, the temperature is that proportionality to motion, right? We never said that the temperature was proportional to anything like potential energy. There's no way that the concept of temperature is going to show up in the fact that energy is like bound up between like all these like forces inside of something, inside of some substance that isn't a gas, like a liquid or solid. Right? That just wouldn't show up as temperature. It wouldn't manifest itself as temperature. It couldn't be delivered out of the substance in the same way because it's contained, it's potential, right? But the gas, the ideal gas, it can't store anything. So it always whatever energy you add to it means it's hotter, which also means it's ready then to actually give up that energy easily. Okay? So most gases behave approximately as ideal gases. Even things like air, which is a mix of many gases, right? Mostly diatomic nitrogen and oxygen, but also trace amounts of other gases as well. So that mixture, sure, that works as well. Up to a good estimate. So if the process is adiabatic, there's a key word for us, no heat flows into and out of the gas. Okay? So an adiabatic process in the context of the first law is just setting the Q term equal to 0. All right, so we got our first named process here, right? So put this on the next page. So in terms of our named processes, number 1, adiabatic process, just means that Q equals 0. Therefore, the first law becomes, so the first law, not Newton's law, but first law of thermodynamics, that's what I'm talking about when I talk about first law here, okay? The first law then simply becomes 0, not 0, but delta U equals 0 minus W. Work, I'll keep using my subscripts. Remind you, this is work by. So that means that delta U just equals negative work by. Right? Because that makes perfect sense. That's a system where there's no heat flowing in or out. Everything that the system does in terms of changing its internal energy can only show up as like mechanical movement. So this is interesting because this requires zero heat flow, which means it better happen fast because there's no such thing as a perfect insulation. So this only applies approximately to things like explosions that happen so fast that that release of internal energy could show up immediately as work, like moving a piston, with no heat flow happening during that movement, the fraction of a second it takes place, okay? Sure, heat would flow out of the chamber, right, whether it's insulated with metal or whatever, but maybe not right away, right, or not on the same time scale as the movement. The very fast acceleration, big release of energy all at once. So that's what adiabatic processes are in practice, but they're nice and simple because Q equals 0, okay? So even though no heat is added, the temperature of the gas will increase, right, in an adiabatic compression, since the internal energy increases. So if you compress something really quickly, you can actually trigger it to change, right? So rapid compression, not allowing for heat flow, can cause massive changes in the internal energy, okay? So that's kind of cool, right? That's the idea. You can like recompress things, right? You can force phase changes with rapid changes in volume, right? Because that's really what work is going to show up as, right? As we go over here and take a look at this, one thing to remember that in the context of the piston and the ideal gas, the work by is just going to be equal to the force or the pressure. We don't have to go all the way back to force and area of the piston, but the pressure, right, times the change in volume, right? So times delta V, okay? So that's it. And let's see, because if delta V is negative, then we have, right, so if it's decreasing, then we end up with work by. I'm going to actually check the signs on yours one here. You did a good job of explaining it. So work done on the system is negative, right? So negative work increases the energy of the system, right? Oh, because if it's decreasing, the change in volume is negative. So if we have, because then it becomes work on, precisely. Where here it's written, right? So here, if delta V is, yes, everything's consistent. Let me go back to my notes, I'm referring to them. So if this delta V is greater than 0, that's an expansion, which means that is going to be the substance doing work, right? So it's totally consistent. So we say if delta V is greater than 0, then expansion, which is just kind of shorthand for then that is an expansion, right? That's what's going on. And thus, work done by the gas is greater than 0, right? If it's compression, if delta V is less than 0, okay, then that is by definition a compression. And this would be the same as work being done on the gas or work being done by the gas being negative. Right? So that's the same thing as work on being greater than 0. Okay? So that's the idea. That's compression, that's expansion, that's what negative volume means. Okay? This means you're losing volume in your confined ideal gas. Okay? There's that. This, by the way, doesn't just apply to adiabatic. It just applies to any case where you have an internal energy and an absolute temperature that have a linear relationship, which is any ideal gas. Okay, which is really great because it means that our internal energy has a meaning that can be converted over to those other systems. Okay, can be related to temperature. So if the process is adiabatic, no heat flows in or out of it. Right. So we mentioned that still the internal energy changes, but then we're going to add to this. Right. This is an example where no heat is transferred, Q equals 0, right? Yet the temperature increases, all right? That tells us that temperature and heat are definitely not the same thing, right? It's a great indicator of that, right? An example, right, an adiabatic process is a perfectly insulated container, right? Another example is a process that occurs so fast that there's no time for the heat to be transferred, like an explosion, okay? So it could be slower if it's perfectly insulated or practically perfectly insulated or just fast enough, all right? But neat kind of like conceptual grounding point of being like, hey, you have this case where temperature changed, but heat was 0, heat flow was 0, right? So there you go, fundamentally different, right? What that means, what do they represent? Well, temperature proportional to the average kinetic energy, it represents that motion within the solid. All right. So other types of processes: isothermal, isobaric. Okay. So isothermal. That means that the temperature doesn't change, right? So for the isothermal, we end up with a delta T that equals 0, okay? But where does delta T show up in the first law? Well, it's not in there immediately, is it? Well, it turns out it shows up in the internal energy. Because if your delta T doesn't change, then your internal energy can't change, as long as you are an ideal gas, okay? Because remember, other types of substances can contain internal energy as potential energy, in any number of ways between molecules and atoms and nuclei, okay? But, well, ideal gases just simply can't, because they're idealized as just particles. They don't do anything except bounce around, okay? So then we say then, all this is for an ideal gas, by the way. So for ideal gases. So it's basically what we're doing here is we're taking the first law of thermodynamics, a more general statement, and we're specifically applying it to ideal gases because of the elegance, because it allows us to express things. All right. So we got our delta T equaling 0, which means thus for isothermal delta U equals 0. So that means that in practice, what the first law becomes for isothermal is just 0 equals Q2 minus work by, or Q2 is exactly equal to work by, okay? So we end up with a system, in the case of isothermal, where all the heat that's being added to the system is being manifest as work, okay? Because that, it means that the system must be expanding, first of all, and it's expanding in such a way that it's not heating up, which is to say gaining temperature. Got it? All right. So the isothermal must, if its Q2 is positive, okay, if it's not cooling down, if it's heating up, it means there must be expansion, because there's no way for this term to be equal to another positive term unless it's getting bigger, because Q and W are both changes. So this is just saying that the rate of change of heat added to the system equals the work being done on that gas as the gas expands. Okay? Okay? So change in internal energy is 0, right? So that means we can rewrite this by just saying Q equals W. Isobaric, by the way, is where the pressure is 0, okay? Well, not 0, but where the change in pressure is 0. Not the pressure itself is 0, but where the change in pressure is 0. That means no work. Because if your change in pressure is 0, that means you can't have you can have a change in volume. I'm thinking isovolumetric. So isobaric is actually the trickiest one. Nothing goes to 0. So if isobaric, all the terms are non-zero, the change in internal energy, the Q2, and the work. But the one saving grace that isobaric has is, since pressure is a constant, that equation that the slides presented, and I wrote down over here, the equation that had pressure and work, all right, and volume. Well, if your pressure is a constant, that means you have a linear relationship, because otherwise your pressure isn't, right? But if your pressure is a constant, then you have a linear relationship between the change in volume and the work. So you just got a nice diagonal line, which means it's really easy to calculate the work being done in the case of constant pressure, all right? But it's still the trickiest system to work with numerically. Isobaric, constant pressure, all right? And the last one that is so trivial, where there's no work at all, is isovolumetric, which just means no change in volume, all right? So all of this is nicely tied in with the ideal gas law. So now we've got the first law, we have it applying nicely to ideal gases, and as if that wasn't enough, ideal gases come with their own law, right? Which is just another energy conservation law, but applies to the way that their pressure and volume is directly related to their temperature. What it tells you is that the product of their pressure and volume is exactly related to the number of atoms, particles there are, times some constant called the Boltzmann Constant, and then multiplied by the temperature. So if you change something, if you have like a delta P, then you just have to put a delta T over here if your V is constant. Conversely, what if you have a delta V but a constant P? Well, that means that you simply go over to this side of the equation, and that delta V will be balanced on the other side of the equation by a delta T. How do I know that? Because N and K are constants. Number of molecules, that's not changing. You're not letting any of your gas out or in. Okay, that's always going to be the case. Okay, and then K is just one of those constants of nature, like the universal law of gravitation constant. That's just called the gravitational constant, actually. Okay. So anyway, this one's called the Boltzmann constant, and they're based on a few, really, fundamental constants: speed of light, gravitational constant, and Planck's constant. So we end up with many of these. Some of them are experimental. Okay. So another form of this equation, PV equals nRT, is more common by chemists, but just fine. It's got a different constant called the ideal gas constant, and which has different units because now n isn't number of atoms, which was unitless by the way, but now is something called a mole. The mole doesn't have traditional base units, but it is considered its own base unit for the purpose of concentration. But that's more a ratio. It is a ratio. It's just a number, right? It doesn't represent anything physical, but sure helpful for concentrations, okay? So that's what a mole is. We won't get into a mole right now, okay? So when a gas is heated in a hot air balloon, the pressure, not the temperature, remains constant, okay? So that's a case of isobaric. The gas undergoes an isobaric expansion, okay? Because you can have isobaric compression as well. Those are your two cases with any of these processes. Compression, expansion, right? That's going to give, right? Every single case except for isovolumetric, where it's neither. In that case, what changes? Well, the pressure goes up or down, okay? So all comes down to pressure or volume, which is hinted at here by the ideal gas law, because that balances one side, okay? Balances one side of an energy conservation equation, just like the first law of thermodynamics. They're all just energy conservation equations. Because literally, by the way, the units, just to reiterate that, the units on both sides of this equation are in fact joules. PV is, that's joules. Pressure times volume is, Newton meters, kilogram meter squared per second squared, units of joules. The balloon experiences a buoyant force, okay, because the gas is expanded, its density has gone down, okay, the density decreases as expansion happens, that drives it upwards. What a neat chain of events, right, all tying in with, processes we've seen, right? We just saw, this idea of thermodynamic processes, the first law of thermodynamics, because you can think of all these named processes, they definitely would fall under the category of first law of thermodynamics, right? So these are things that are associated with the first law. These are applications of the first law of thermodynamics. So we did that, okay? Then we applied the ideal gas law, all right? Then we applied that to that's this part right here where we affected the density, all right? I guess we applied the definition of density. Then we applied the buoyant force, okay? Then we applied just Newton's second law to come up with the fact that there must be an acceleration, because you can't get rising without an acceleration, because you had to accelerate from rest, at the very least. Okay, so to wrap up this lecture, we'll talk about the three mechanisms of heat flow. There's not going to be any equations to wrap this up. These ones are entirely conceptual. So your one major equation from this second half of chapter 10 is definitely that first law, okay? Sometimes used in tandem with the ideal gas law, all right? So that's the one you got to get a handle on. You can only do it with practice. But let's wrap things up with the three ways that heat flows from point A to point B. And that's the way I always put it, because that's kind of the question, is we've talked so much about heat, quantifying it, relating it to other forms of energy. Great, okay? But at the end of the day, it does move from one place to another, right? We know things warm up, right? So that means that it turns out there's only three ways that heat actually has a mechanism to move, which are conduction, convection, radiation. What are they, okay? So conduction is the heat flow through a material when objects at different temperatures are placed in contact with each other. So it's a direct contact way that heat flows. It requires some short distance molecular contact. So it's things vibrating, jiggling around, that ideal gas, right? Bouncing into the wall. When it bounces into the wall, it causes movement within the wall on this atomic scale, right? Molecular scale. That's actually what's happening, okay? Right, so for conduction, the rate of heat flow depends on the temperature difference between them, okay? It also depends on the thermal conductivity. So different materials conduct heat very differently. Insulated materials have heat flow through them very slowly, right? Sometimes to a point that it's not really going to flow through them unless they're surrounded by some insulation, because it's able to escape through some other mechanisms along the length of that material. So for example, a metal block, right, at room temperature will feel colder than a wood block at room temperature. So that's a neat one, because we usually think about things being a good conductor heating up fast. But when you touch these two objects, right, that were just sitting there, you're warmer than the room around you, being this warm-blooded organism. That means you're touching two things that are colder. But the wood, okay, the wood is essentially, it's not going to conduct very quickly, so it won't cool off your hand, okay? So you touch the wood, it doesn't really feel like much. You feel the roughness of the wood, but you don't feel any noticeable temperature. It doesn't trigger your nerves that respond to temperature differences. But when you touch the metal, that immediately starts sapping energy away from your hand, because you're flowing from, the energy always flows from high heat, high temperature to low temperature, okay? Which we'll talk more about when we officially present the second law of thermodynamics, because that's actually kind of one way to paraphrase it. But regardless, you're touching something, heat's flowing from hot to cold, okay, to the metal, right? In both cases it is, but the wood's such a bad conductor that you don't notice it. With the metal you do. So the fact that the metal feels cold is literally because heat is flowing out of you more quickly. That's what makes it feel cold, all right? Now, that doesn't mean eventually it would reach equilibrium with you, and it does. If you, left that metal on your skin for a while, it wouldn't feel cold, okay? Because it would reach equilibrium, okay? All right. So the other way that heat can flow is convection. One of the other ways, the second of the three. All right, this is heat transferred by the motion of a fluid, okay? It's often called the bulk motion of fluids because it isn't considering the, kind of something happening on the molecular scale like conduction was ultimately. Convection doesn't work like that, because convection, if it was on a molecular scale, maybe we'd be assuming that all the molecules are moving around independently of each other. But that is not the assumption with convection. It assumes movement of many molecules in tandem, creating big structures like rising plumes, like in a lava lamp. Or if you've seen representations of the flow of magma underneath the Earth's crust, that you see those convection cells. It's often shown with weather as well, that vision of hot air rising, cold air sinking. Of course, we see that in the room here, right? So this is shown as a cell, in the sense of, like a square of rising and sinking air, hot air rising because of its lower density, same reason the hot air balloon rose, but not contained air, kind of freely mixing air, as a large circular structure, a bulk structure, a vortice, and a, some sort of circular thing, all right? It's the main method that heat is lost from buildings. Convection is a big deal in our atmosphere here on Earth, okay? Now, radiation is the only way that heat can flow through a vacuum. Huge deal for astronomy, huge deal for physics. It kind of, understanding radiation leads to understanding light, which ends up tying into kind of being a capstone understanding of electromagnetism. Talk about cool interrelated ideas. But here we're actually just going to appreciate radiation as a way that heat flows, that Q term, measured in joules. But man, we're going to talk about it more later, because we are talking about light, right? So the electromagnetic waves involved in the transfer of heat lie primarily in the infrared portion of the spectrum. That's what we think of as like a heat lamp, or the heat from the sun is the light that we just can't quite see because it's too short, or too low frequency, too long wavelength, too low energy. That's infrared, right? Outside of the visible spectrum. We'll talk more about the spectrum later. Unlike conduction and convection, which both require a medium, right? In case a fluid for convection, it can be a fluid for conduction as well. By the way, fluids and gases, liquids and gases, fluids collectively, but especially gases, aren't great at conducting, as you would expect. Closer packed together molecules or atoms are better at conducting, right? Delivering that heat through direct contact. So, but they can still conduct, okay? So a perfect vacuum can't conduct at all. It also cannot convect because there's no fluid to move. The only way the heat can move through that perfect vacuum is as light, okay, which is that electromagnetic phenomenon packed in little particles, as quantum mechanics tells us, called photons. But whatever it is, it's light, okay? And it bounces around. It can be reflected off of reflective surfaces. It can travel from the sun. It can be absorbed by absorptive surfaces. Most light that we see is reflective, but there are sources of light as well. In fact, as we're talking about right here, anything that feels warm is a source of light, right? But it's not light that our eyes can see. There are some organisms that do see us, right? And if you put on heat goggles that are, changing infrared into usually shades of green or something, then you can essentially see that heat, or you can see a conversion of that heat done by a special sensor, right? And a circuit. So which process makes a car's interior heat up when parked in the sun? So what do you think? Car's parked in the sun, talking about, what's happening inside the interior, seats feel really warm. What is that? All right? Definitely radiation, right? Light is transparent through the windshield. Interestingly, the car gets extra hot because you have light, visible light coming from the sun, a source of light, right? Because of nuclear energy, comes down through the atmosphere, a certain amount makes it through the atmosphere. Bunch comes down though in the visible spectrum, passes right through glass, because glass happens to be transparent to basically that, right around that band of the visible spectrum, hence our interest as humans, visible spectrum seeing organisms. We like glass, right? But it turns out glass is opaque, which means doesn't let through light that is longer wavelength, like infrared light. Well, that's the type of light that the warm seat is glowing in, literally glowing, releasing light. But that light gets bounced right back off the windshield, creating a greenhouse effect. It's trapped in the car, all right? So that idea of trapping things in is just, you want opacity to some wavelength. Now, it's like a big thick wall of insulation is opaque to a lot of things, right? Even infrared, right? Even visible, I should say. Okay? So then you can have a certain way of quantifying the insulation. I'll skip over to this a bit. Okay? All right, but the greenhouse effect I was talking about, plastic, right? Transparent to visible light, okay? But not transparent, opaque to infrared. Traps it in. Turns out there's certain molecules like ozone, but especially, ozone's more for absorbing X-rays, or rather absorbing UV, especially high energy short wavelength UV. Ozone does that. It's a bit of a greenhouse effect, kind of also bouncing off infrared. It's not particularly transparent to it. But CO2 is very, very much, as is H2O. H2O is probably the biggest, methane as well. These are gases that effectively act like a sheet, like glass does, and they allow in visible light, so some particular type of radiation, heat, right? In the sense that it's moving, that is energy moving from one point to another, because that's what heat is, right? It isn't moving as mechanical or some other form. And so it's coming in, right? And it comes in, and then it's going to get trapped because the infrared can't pass back through that sheet of carbon dioxide. That's the same thing that glass does, right? With the same types of light, right? Right. So hence the name, right? The greenhouse, because you have a glass house, greenhouse. Okay. So I think that's a great place to wrap it up. I hope this discussion on the first law of thermodynamics, just talking a lot about these systems, about changing from one form to another, is kind of like starting to come together for you. I'll leave you with a couple of visualizations, which you probably saw as I was moving the screens around. This one here is showing a kind of a cartoonish representation of a bunch of trapped molecules. Okay, and we can actually choose any temperature and have it be locked at that temperature. So you can lock it at 100 Kelvin, 200 Kelvin, 300, 400, 500, 600, right? If you lock it at 300, that's closest to room temperature, because that's like, room temperature is like 293 Kelvin, as in like 20 degrees Celsius or 70 degrees Fahrenheit. But regardless, right, so we lock it, right there. Right? That means the temperature won't vary. In other words, what I'm showing you is an isothermal process. So if we reduce the volume on the slider, because that's what you can control independently, well, if we're keeping the temperature the same, something else will change. What will change? The pressure, okay, from the ideal gas law, and it will change in a very predictable way. See, look, it follows this curve. This curve is actually called an isothermal curve, and it's on a graph that shows pressure, right, in this case measured in kilopascals, right, versus volume measured in liters. So this is a pressure volume graph, sometimes called a PV diagram or PV graph, and it's the best way to show any of those named processes: adiabatic, isothermal, isobaric, right? If we look here, this one is actually over here. We have, this one has different, so this is the same one. I had one that had a few different examples of different PV diagrams. There you go. All right, we'll head over to this one then. Okay, so this one's a bit more complicated, but what it shows us is more of these processes by name, which is nice, because before I was just showing the isothermal one, but there's no name showing up. So if it's moving from the left to the right, that is an expansion. We know because the vertical axis, just like the last one, because they're all going to be the same, they're all PV. The horizontal axis, fumble there. The horizontal axis is volume, all right? So if we're going towards the right, then we're going towards increasing volume, okay? So any movement to the right, shown with arrows, is a expansion. Anytime we go in the direction of the left, in the horizontal direction, that must be a compression. Now it's possible to have something that's neither a compression nor an expansion, like going from point 2 here to point 3. Zoom in a bit. So that right there, that's that process, the one that was so unimportant it wasn't named in your slides, which is the sometimes called the isochoric. I call it the isovolumetric. Both are acceptable, but it just means constant volume. All right, and we actually have 2 of them shown here, from 2 to 3 and from 4 to 1. Now, if you hold volume constant, the ideal gas law tells you that as a result, something else must change. In fact, two things will change. The pressure and the temperature will change. Okay? And we know that the temperature will change because you'll cross an isothermal. You can actually add isothermals for this particular substance, some ideal gas, right? And it will show these different values, right? These are curves corresponding to 5800 Kelvin down to 200 Kelvin. Okay? And we can see that if you have a isochoric, now I'm calling it that, a constant volume, right, decrease in pressure, that also would be a cooling. Okay? Now remember, right, there's also that case where if you did something really fast or perfectly insulated, then it was called adiabatic, which was where the Q term was 0. Well, those show up as well. They're called adiabats, like, you know, because they're referred to adiabatic processes. And you can see that they're most kind of meaningful if you look at them compared to isothermals. So we see they're steeper. Because if you have an adiabatic expansion where your Q term is 0, no heat is entering or leaving the system, then you would follow this red curve because you're expanding. You'd follow it to the right because you're expanding. But notice you cross an isothermal, particularly the red curve is steeper. That means that it always results in some cooling. So adiabatic expansion does result in a decrease in the change in internal energy. Okay? So there must be some cooling. And you could quantify the cooling for an ideal gas. Okay? So all, kind of neat representation of all these processes on one graph, which means that it's great in terms of you can do everything on a single graph and get all the ideas and see how they're connected, but also means it's upfront a little intimidating, right? Because you got this shape and you can choose different processes. Let's do a isochoric. Oh, I got it to be a mess. There we go. That's then down to 3. How about that? Fixed a bit. Still. I want the point up there though. So simulation's having a hard time. Oh, there we go. I need to put the point there. Perfect. All right. So this is just 3 processes, right? Isobaric, that's a flat one there because the pressure is constant. Baric, like barometer, right? Then we have the isovolumetric, going this way. Actually, we're going back this way. Okay. And then this one here, this is an expansion. And it is it's an adiabatic expansion. Cool. Well, which makes sense because it's on one of the red, or it's kind of got the steepness of one of the red ones. It's on the red curve. They shade out the red curve when you choose it. Cool. All right. So there's an example. When you create a cycle like this, by the way, I'll mention this again in the next chapter. That shaded area inside is either the work done by the cycle or the work being done on the cycle, depending on whether it's clockwise or counterclockwise. So hopefully that's kind of a cool teaser of creating an engine out of this pressure volume understanding of thermodynamics. And with that, I'll finally wrap things up and say thank you for watching this video. I hope this conclusion to chapter 10 has been interesting and informative.